All right, here we go. Electronegativity. This is a big daddy idea here. All right, we'll go through it pretty quick though. So if you remember, we have ourselves protons in the center. We have electrons in the outermost shells, or the shells. And then we have electrons in the outermost shells, valence shells. Now, we're not worried about the numbers right now. Remember, these protons, positive charge, are attracted to the electrons, negative charge. Since these are protons, positive charge, electrons, negative charge, they attract each other. Now, we already talked about ionization energy. Ionization energy is the idea that this positive charge is attracted to this electron, and the amount of energy required to remove this electron away is what we call the ionization energy. The greater the positive and negative attraction, the greater amount of energy is going to be required for something to come by and remove this electron away. Now, using that same idea, this positive charge is attracted to these electrons, but it doesn't stop at the atom. It doesn't stop at the edge of the atom. This positive charge, its attraction abilities are going to go beyond the atom. It's going to go beyond the atom. Can think about music. If I have a radio playing and I'm putting it in my backyard and it's playing it in my backyard, the music doesn't stop at my fence. The music's going to go beyond my fence. And somebody literally right across the street might go, hey, I'm jamming out, I can hear the music too. And so what happens is that or smells. If I'm cooking something in the kitchen, the smell doesn't stop in the kitchen. Or if I'm with my wife, I'm attracted to my wife, but her attraction doesn't stop with me. If she's able to attract me to her, there's a very good chance she's gonna be able to attract other people to her as well. And so it doesn't stop at that edge. This positive does not stop at the electron. So what does that mean? The greater the ZEF, the effective nuclear charge. So if this is 9 protons, 2 shielders, we have a ZEF of a 7. The effective nuclear charge is a 7. That means that it's going to hold on to its own electrons really tightly, but it also has the ability to grab onto an electron being held onto something else over here very, very strongly. Is going to be able to possibly bring that electron in and add it to its own shell, if there's room. If there's room. We'll talk about that in a sec. If there's room. And so as a result, we would say that elements with greater ZEFs, effective nuclear charge, are going to have a greater electronegativity, the ability to bring electrons to them, to attract electrons in. Come back to our handy dandy little chart. That means that these guys over here, low electronegativity. They still have some electron, but low, because they have a small ZEF. We come over here, high electronegativity, except for noble gases. Noble gases. Why? Why noble gases? Why are they unreactive? Because here's neon. 10 protons. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. Ooh. We've got 10 protons pulling in, 2 shielders. We've got a ZEF of 8. So that means it's got a huge ionization energy. The ionization energy is huge. So somebody can buy too much energy to try to pull an electron off, unreactive. But you go, well, why doesn't it gain then? Why can't it gain an electron? The reason why is because the electrons won't fit into the second energy level. It's just not big enough. Just not big enough. Electrons won't be able to fit in there. Too much repulsions. And so theoretically, let me draw it in a different color. Theoretically, in order for neon to gain an electron, it would have to be in a third energy level. And you go, so what? And now, that electron in the third energy level, we would have 10 protons in the center, 10 shielders. In order to put an electron out here, we'd have a ZEF of a 0. It wouldn't be able to hold on to that electron. So it can't gain an electron because it'd have to theoretically be out here. and it can't lose an electron because the Zeph here is 8. It's too much energy to remove it. So we say that noble gases are relatively unreactive. Listen to the word relatively. Can react. In fact, as you go down the periodic table, these guys become more reactive. They more covalently bond. Why? Because the distances get greater. And so we're able to get a little sharing going on down here. We'll save that for another time. All right, that's it.